Okay, would you let me know if that does it again? All right, gang, sorry about that delay. So if I could just show you what's going on here. When you have a solid that's trying to dissolve and make a complex ion, there's going to be two chemical equations that are happening. One of them is the solid is trying to dissolve. And this is exactly what we saw on the previous slide, where there's no help from anything in the first equation. It's just silver iodide brute force trying to dissolve. It's not going to be very successful, as we noticed from the K value. But when we have a ligand, this is not the only thing that's happening. These very few silver ions that are present, if there's ammonia molecules, the ammonia molecules are going to come along and bind themselves onto the silver to make this complex ion. And what that does to the first equation is we're removing silver ions from that equilibrium, which drives the reaction, that first reaction, that way, and causes it to dissolve more. So what is the overall solubility? We're going to have to wind up adding these two equations together because they're working together. So adding these two together, notice the silver ion that's produced there is used up here, so that winds up canceling out. And we're left with AgI, solid, plus two NH3s, yields this complex ion AgNH3 taken twice. It's got a positive charge. Silver is positive 1, and then two neutrals still gives us a positive 1. And then iodide ion. Now the K for this reaction overall, we multiply those two together. Can you do this without a calculator? Would you be able to multiply 1.5 times 1.7? I think you can. When you're multiplying 1.5 times anything, you do it in two steps. Multiply this number by 1 first, 1.7 times 1, 1.7. And then you have another 0.5 times 1.7. What's a half of 1.7? 0.85. So you take the 1.7 from multiplied by 1 plus the 0.85, and you'd add those together, and it's like 2.6. Yes? So it's 2.6 is that product. Why are you responding? You can do that. Practice. 1.5 times anything, you can work on that. And then you just add the powers on the 10, which unfortunately, because this KSP is pretty small, and that K of formation is not very impressive, really. I mean, it's a nice K. We're used to K of being 10 to the negative power. But when you couple it with this one, we still wind up with a 10 to the negative 9. That's a bummer for the K value for this thing. So still it's going to favor the reactants, but it's going to be better. Better than trying to dissolve silver iodide just in pure water. Let's go ahead and do the ice table on this thing. And by the way, I'm just going to make a comment too. I had shown you, now yesterday we just had a half day and we didn't talk about ice tables. I guess we did because we talked about hydroxides. But the day before yesterday, I told you sometimes we need a modified ice table. I called it an ICE table, I-C-C-E, right? And an ice table like that modified one, that only is used when the question asks you for what is the final concentration of ions after they have been mixed together and made a precipitate. That's not what's happening here. So just to try to address any confusion you might have about when do we use an ice table and when do you use an ICE table. We always use an ice table unless we're trying to figure out the concentration after precipitation. You'll see that, so keep that in mind as you do some of the homework exercises. You'll need a modified ice table only in one type of problem. This is not it. All right, so anyway, this is just ice and solid. We have an initial concentration of ammonia, it's 3 molarity. And then that's 0 initially, and that's 0 initially. So then this reaction is going to go to the right. The silver iodide will dissolve a little bit, and as it does, this is going to go down by 2x. And these both go up by x. Yeah. Now the silver iodide is still a solid. The NH3 is 3 minus 2x, and these are both x. So the question is, what is the solubility? We're trying to find this term right there. So when we solve for x, that's our answer, the solubility. So doing the calculation, our K value is 2.6 times 10 to the negative 9th. And that's equal to x squared over 3 minus 2x. And that quantity gets squared because it's got a 2 coefficient. Do we need to worry about neglecting anything here? We worried about that yesterday with the hydroxide. Remember, you have that initial concentration hydroxide? Is that an issue here? Take a look. What do you see that's real nice about this math? The right side is a perfect square. X squared over that quantity squared. So that's not, we just take the square root of both sides. Try to do it without a calculator. 2.6 times 10 to the negative 9th. Can you take the square root of that one? I think you can. Because 2.6 times 10 to the negative 9th is the same thing as 26. If I multiply this number by 10 and I divide that number by 10, it's still going to be the same number. Yes? So this is 26, and that's 10 to the negative 10. Well, 26 is really close to a perfect square. It's 5, right? The square root of it is. So 5 times 10 to the, and if that is 10 to the negative 10th, it's just 10 to the negative 5th.
Are you such a math guy?
No. I just like to practice. No, not at all. But I do just encourage you to try to think about numbers and what your brain can do with them, and I think you'll be surprised. All right, so the right side, let's take the square root of the right side, and then we can all feel like we're pretty good at math. Square root of that is x over 3 minus 2x. Now we have to grab our calculator, I think. Can you get an x? What's the? We could probably do that. I mean, 15 times 10 to the negative 5th, and 10 times 10 to the negative 5th x. If you have an x, would you just yell it out?
Is there going to be that kind of math on the test?
Maybe. I think this would be a stretch. For me to give you this kind of thing, say, hey, take the square root of that, I'm not going to do that. But if I gave you 2.6 times 10 to the negative 10th, or no, I wouldn't give you that. If I gave you like 9 times 10 to the negative 10th, and I said take the square root, I expect you to be able to do that. This one, that's asking a lot. Are we friends again?
Yes. We've always been friends.
Oh, yeah. Okay. Thank you. What do you get for x? You get something times 10 to the negative 4th. 1.5? X equals, thanks, 1.5 times 10 to the negative 4th molarity. And I admit myself that this does not impress me at all. I mean, all this work we did, we're dissolving this silver iodide, a very stubbornly not wanting to dissolve solid. We put it into a complex, into a ligand solution, hoping that the ligand is going to actually improve its solubility. But then at the end we get that. And I think, well, that's kind of anticlimactic. It's still terrible to dissolve 1/10,000th of a molar. Yay. Right? It's still very, very dilute. However, when we compare it to what it was at the beginning, it has gone up in solubility by 10,000 times. I guess we can't turn our nose up too bad. Yes? So you do see, hopefully, that with the ligand, the solubility is improved. It does dissolve better in the presence of ammonia, because the ammonia can make a complex ion with it, which is very soluble. Now, I'd like to show you a couple of formations, like real formations of complex ions. I'm gonna just take this and hey, look, guys, look who's back after she's had a bit of a leave. Hi, Sajid. Let's see, Rishi, would you hang on to this for me? That's right. You're gonna be signing autographs before too long. I have no safety glasses, so maybe I shouldn't put this on yet. I gotta protect myself. Protect the image.
How do you do it? I mean, look at those biceps.
And earlier today, I was offering to anybody to smell the ammonia. Again, you remember smelling the ammonia? But we're not doing that on camera either because I'm like a suit. So, I'll just behave myself up here. And I have some copper 2 sulfate. Copper 2 sulfate. The copper 2 ion is blue. And if I put some copper 2 ion into here, adding to the copper sulfate is a dilute sodium hydroxide.